Hey there, I'm Ali, and this is a short promo video on my research project, an inverse kinematic approach to the reset mechanism. In this project, I redefined the reset mechanism in a reinforcement learning framework. Instead of using the instant default reset mechanism provided by most robotic simulators, I redefined it so that it's not instant anymore, but uses an inverse kinematic approach to reset the environment as intended. Why would I do such a thing? I hear you ask. Well, in general, there are two approaches to deep reinforcement learning model training. First one is real world training. A robot that learns directly from the real world can perform its task better and better as it gathers more and more data from the real world. Problem with this approach is that it cannot do this without substantial human intervention or engineering. Second one is simulation to real world transfer. A simulation of the robot and its environment is first constructed, then the robot learns the desired behavior in the simulation. And then the learned behavior is transferred to the real world. This approach has some fundamental drawbacks. The simulation will never exactly match the real world, meaning that improvements in simulation performance might not translate into improvements in the real world. And if a new simulation must be created for each new task and environment, content creation can become very expensive. Training robots in the real world eliminates these drawbacks, but is much more challenging due to certain limitations. One of these limitations is the lack of the reset mechanism. Reinforcement learning algorithms almost always assume that an episodic reset mechanism exists, which resets the state of the environment to an initial state. This allows the agent of the robot to try the same task many times from the same place. But in the real world, this reset mechanism does not exist and must be engineered somehow. There are alternative approaches like the reset free learning from Berkeley University, but they also come with their own problems, like getting stuck in a certain state for too long, for example. So, what exactly did I do? Well, I redefined the reset mechanism using inverse kinematics to eliminate the drawbacks of the reset free learning method. With, with each call of the reset mechanism, the position of the object is given by the simulator to the inverse kinematic algorithm. In the real world, this would happen through an object detection algorithm. The inverse kinematic algorithm is in turn manipulates the robot arm to set the end effector to the correct position and moves the object to its initial position to go to the next iteration or episode. So my final results, I'll show you my final results. Up. So my final result is a robotic arm trying to learn to pull a box to the goal position, which is located 0.5 meters from the initial position of the box. So that's like at the start of or the beginning of the table. The robotic arm will eventually come in contact with the box, which means that the box has to be reset to its initial position. The robotic arm will use inverse kinematic and trajectory planning to push the box to its initial position in the next episode. So let me show you that. So I will push the box a little bit to the goal position, but not exactly at the goal position. So now it's still training. So but at some point it will see that the box is not in its initial position, and then it will use inverse kinematics and trajectory planning to push the box. Let me see. So it will do that at the next episode, basically. Now. So now it's putting the box back to its initial position. And then it should restart the training. The problem with this approach is that when the box gets out of the workspace, there will be no solution for the inverse kinematics of the robot configuration. So when that happens, I made it I use the default instant reset of the simulator because there's no other solution, because the robotic arm will not be able to reach the box. So this project proves the possibility of an inverse kinematic approach to the reset mechanism, but it also shows that it comes with some constraints and impracticalities. So thank you for listening, and see you during the presentation.